Good afternoon, everyone, and thank you for joining me in this session where we will talk a little bit about machine learning, traditional machine learning. Almost feels archaic for solving some business models that we had over the past few years in predictive maintenance and fault diagnosis. To set the stage for our talk, I want to ask you to all imagine a clinical setting. Show of hands if anyone here has experienced or had heard about long hours of waiting in hospital emergency rooms. I see a lot of hands up, and that's actually one of the issues these days. But how do we feel if it was doubled, tripled? Pretty awful, right? And that's why that medical equipment and anything that contributes to patient safety cannot just go down. It needs to keep working and not stop working. So what happens if one of these medical equipments are down? We would see that the instruments that needs to be sterilized to keep the patients coming and have them treated are piled up, and we would see that the dentist or clinician in this aspect would have a lot of anxiety because they don't want to put the patients in danger, and they also want to keep the revenue and keep the business running. I actually had the experience a few months back where my dentist called me and said, "We need to reschedule you. We just simply cannot have you in the office because our sterilizer is down." And what happens here is that the dentist would call their technicians and they ask them to on demand and come and fix it. But then in these scenarios, the technician would say, "Hey, my people are on vacation. I'm actually can only help you in a few days." And even if they have people on demand to send and the technicians would be able to run a few tests, maybe or maybe not, they can fix the problem. They might say, "Okay, look, I don't know really what's going on. I have to take it out if it's small enough and treat it in the shop and see what's actually going on." So how can we fix this problem? Should we hire more technicians and maybe not give them any vacation times? That doesn't really sound realistic. And being at an AI conference, I'm sure that you know what I'm trying to build up to. What AI can help in this use case is that using AI can actually help us to diagnose a problem much faster and even predict a failure before it happens. Think of it as a check engine light that shows up on your car's dashboard when it's going to go down, so you would know in advance that I need to get it checked. Now, with that introduction, what I will talk today about is that I will take you through how we can go from a reactive maintenance to a predictive one. What are the success stories in the medical equipment industry in implementation of predictive maintenance? I'm going to tell you what we did in CICAN and what we learned and what we are doing right now. And the most important part, we will talk about regulators, because at the end of the day, it's important to stay compliant with the regulators. And then we'll talk about what's going to come next. So I remember a while back, we bought a pretty expensive TV, and it had a 1-year warranty. And right at the 13th month, I started to see a dead pixel in the middle. So I was pretty much in denial, and I thought, okay, that's me. It's going to go away on its own. To my surprise, it actually grew and expanded, becoming a line. And before actually I called for technician and support, it was too late. That's the same thing that happens in medical equipment. You see product health degradation, and at some point it would just come to a complete stop. I want you to look at one of the temperature versus time series that we have here. You have a pretty much good flow on when the product has a good health, and then you start to see these peaks and these valleys that could raise a red flag on the product health, and that could be used in advance so that we can predict and we could prevent the machine to go down completely. And that's very important because, like the TV, maybe it's just a dead pixel at the beginning, but then it could grow and damage other components that then causes the whole cost to go up for this repair to happen. And that will come out of the pocket of the clinician or the company that is providing the warranty of the equipment. And in the traditional context of preventative maintenance, that tells you, hey, have it checked every 500 cycles, have it checked every 6 months. That maintenance could come quite early when the maintenance is not really needed, or quite late when it's actually not helpful anymore. So we are talking about cost, we are talking about how this actually makes sense, but let's talk dollars and cents. In the industry, we have seen that GE Healthcare has implemented their predictive maintenance for their suite of imaging equipment, and they've seen a considerable 35% decrease in downtime. That translates to approximately $1 million on average in annual savings. Same experience with Siemens tells us up to 70% of unplanned downtime and 43% cost for on-demand need that the clinicians needed. EBM, which is an infection equipment company, reports that in the UK hospitals, their system actually saved $2 million in savings per site. So these numbers actually tell us that although this technology is not new, it can help not only save us money, but also make sure that patient safety stays a priority. Now, I want to tell you a little bit about CiCan. How many of you have heard of CiCan before? I don't see any hands. Okay, good. For decades, it's been a mission for us to create and develop medical equipment machines that they just run. As a Toronto-based developer and manufacturer of equipment in the infection control, we have a suite of products that are compliant with major regulators. Having that compliance, it allows us to sell our products around the globe. And having these machines IoT-enabled and sending their data encrypted to the cloud, it actually allows us to create digital twins on the cloud of these machines that would basically be the infrastructure that we need for an AI workflow that we are talking about here. And when I talk about the AI infrastructure on the cloud, what I'm talking about is something like this, where you get the data from the cloud by these machines from different means, you store this data, you get this data to be processed and prepared for inferences, and that inferences would be displayed on a dashboard to our technicians or raise those red flags that we talked about for the technicians to attend to the machines before they fail. They can also provide us with feedback. This feedback, along with the monitoring that we have on our AI models, triggers a retraining job whenever we have a model or data drift that would help us improve and maintain the quality of models. But let's take a look at how it actually looks like in action. This is the landing page of our COLTENE website, where technicians can log in and access the machines that needs their attention or interact and find helpful tools for their work. On the left-hand side, we have a monitoring page that they can go to that monitoring page, see the units that have problems and needs their attention. And once they open these machines, they can see a blue robot icon that allows them to open the predictions for that type of failure. And they can close this ticket, providing feedback, a thumbs up, a thumbs down, provide also a feedback in terms of what they thought and what they diagnosed the problem to be, and what they did to fix that problem. And when they actually do that, they can also see that the blue robot head turns green, just for us to have a little bit fun there. But how did we get here? When we look at this image, it's a cumulative temperature values from different cycles of a certain machine experiencing a certain failure. It feels chaotic. It overwhelms you at first glance. But we needed to uncover meaningful information from this pattern. And we needed an unsupervised learning algorithm that would allow us to uncover these meaningful patterns. But we just couldn't use Euclidean distance measurement because there are sometimes a shift in these patterns and they don't usually match one-to-one. Looking at these two patterns, a human might just cluster them in one and say they look the same, they are the same. But Euclidean would say it's not really the same. Imagine you're singing in a karaoke and you're off note and everyone's kind of say, okay, you're not really that good, but you are hitting those notes. And what we used was dynamic time warping. The dynamic time warping doesn't penalize those time shifts and allows you to actually categorize these patterns in same clusters. And even if you're not really good at hitting those notes in karaoke, it gives you a thumbs up. You're doing good. But let's see what actually is happening under the hood of DTW. Basically, what's happening is that it's looking at these two patterns, looking at data points from every pair of these sequences at time index I of the first sequence and the value of, let's say, temperature in time index J of the second sequence. And then calculates a local cost of what is the difference and how it would cost to align these two patterns. And looking at the heat map, the brighter parts are the parts that have a higher cost of aligning these two patterns. So end of the day, we will get a matrix that would allow us to calculate, to find a path that has the cheapest cost to align these two patterns and gives us a total cost of how much it costs to align these two patterns. With that, we would be able to calculate the total cost of every pair of these sequences and put them in a cluster when they are very similar. And what happens in the equation on the top and the bottom left is that it would let us find a representative pattern of these clusters that we make. The end result of that chaotic image that I showed you that almost looked like an abstract painting is an art gallery of different clusters that have similar patterns. And that red pattern is the representative pattern of that whole cluster. But how can we use this? From this point, we actually try to narrow down these patterns and clusters into some meaningful patterns that can be correlated to a component failure. And when we know what is the component failure, we would be able to use supervised learning to predict and diagnose what is going to be the reason of a failure of an unseen new pattern. That's how we started our work in supervised learning. And we use different algorithms to see which one of them is giving us the better performance with the lowest cost of training. From our experience, we saw random forest and XGBoost performed almost the same, but random forest was actually 10 times more time-consuming or more expensive to train. But we ended up going with random forest. The simple reasoning was that we saw that the random forest predictions were closest to the 45-degree that basically tells us it's giving us a better prediction for the compromise of cost of training that we have in the beginning. But let's do a recap. We uncovered some meaningful patterns from our chaotic image. We trained machine learning models to diagnose the failures. And now we are able to understand the product health and compare it to the patterns of failure that we have. It's all roses and sunshine so far. But the problem is that being in a regulated industry like the medical equipment industry, we need to stay compliant with the major regulators. And they have been also very active in terms of providing us with what we need in terms of compliance with regulation. So I'm going to show you a timeline of how it's been evolving and how regulators are getting that acceleration on providing guidances to medical equipment manufacturers. 2021, it was the year that FDA came up with a plan of that they need to have an action plan to provide guidances to medical equipment manufacturers. Later that year, the three agencies of FDA, Health Canada, and UK MHRA provided 10 principles on good machine learning practices. In 2023, cybersecurity becomes law. This might not be necessarily related to our context, but gives us a playbook of how cybersecurity, that is an emerging need for all the companies, became law in less than 2 years from the very initial guidance. We saw in 2024 that FDA provided a draft guidance for predetermined change control plan. I will talk a little bit about this, but it was basically saying that if you are deploying machine learning models in your equipment and you want to update it for any reason, whether that's model or data drift, you need to provide a plan for risk mitigation. Excuse me. And having the PCCP in place would make you not need to get further FDA clearances. We also are seeing a lot of regulators are providing sandboxes for manufacturers to play around and find the right risk and also develop their models in safe environments. 2025, we have seen a lot of development. FDA published a guidance on total product life cycle, TPLC, citing it more than 40 times in their guidance. Health Canada provided in February a final guidance for machine learning on medical devices. And later this year, EU is going to enforce the AI Act. So what we can see is that it's a lot of acceleration. And FDA says that it has already cleared 1,000 medical devices that use AI, but none of them are Gen AI, simply because of the risk, the explainability, and the transparency of Gen AI models. So if you look at how the world is converging, we can see that they are all going toward what FDA published as total product lifecycle management. People in the medical industry are already familiar with this concept when they are releasing software to the market. And FDA is saying it's the same playbook, it's the same checklist. You need to go through a cycle from your design to the retirement of your model. And you need to have rigorous documentation. You need to assess and mitigate risk. And you need to keep monitoring your model's performance even when it was deployed. Thanks to Gen AI today, Our documentation process is quite streamlined and happens in few minutes, when back 5 years ago, it was a month and a half of a whole team working toward it. And it also tells us about total product, in total product lifecycle, about the PCCP. As I mentioned, that if you provide it in advance, then you don't need to seek further clearance when you want to release an updated version of your model. Around the world, all the regulators are telling us the same thing. You need to be transparent. You need to give us all the detail to your models. We are not trusting Gen AI yet. And you need to follow the same processes of releasing a software as a medical device in AI as a medical device or in a medical device. What's going to be next? We talked about how we got from the reactive in terms of, first of all, diagnosing the problem, to predictive, where the customers don't have to wait for a technician to resolve the problem with their machine that could sometimes take weeks or months, depending parts availability, technician availability. And we are bringing value to not only the patient safety, but also the industry in terms of keeping the uptime running. And the next is going to be prescriptive. But what does that mean? We are in the age of AI agents, right? So let's say this prediction can be fed into an AI agent who knows about the FDA ISO limitations, can have access to the data of the machine, can make a decision on maybe running the valve, a certain component, a valve, at 70%, that maybe elongates the cycle time by 10%, but runs the machine for 2 weeks more, while maintaining the integrity of sterilization or infection control. But that also needs regulatory guidances. Having Gen AI to be as transparent that would not pose a risk for patient safety and could actually get the compliance with regulators. With that, I want to finish, and although I'd love to take all the credit for myself, this has been a team's effort from great people that we have at COLTENE. And we would love to hear more about what you thought about this presentation, how we can improve. We try to measure and improve based on data that we. And that's it. Thank you very much. I'll answer any questions.
Thank you for your presentation. I want to ask the metrics of the model. Did you check for overfitting? Because the numbers are too good to be true. Yeah.
Yeah. Okay. Very good question. And yes, so the performance measurement that we had was on unseen data. And why you would see such a pattern that looks like overfitting is because we are using data that is for a robust type of performance that the machine has over and over again. But that said, we keep monitoring the models in the production and making sure that those predictions that we have versus the feedback that we get from the technicians would make us basically providing real prediction, not overfitted, say, hallucination. How big was our data set? The one that I showed you here was only temperature versus time, right? But that cluster also includes 32 other parameters of different sensors, different component status that we had, like if it's a pump on, off. But this specific clustering had around 700 cycles of a specific cycle for a specific machine. And basically the data would be time series of an hour for each one. And then we had a training 70-30%. Based on the, for supervised learning, we basically labeled all these patterns, comparing them to the component failure, whether it was a, I don't know, pump failure, right? And then each of these patterns, the whole 1 hour of it, would be separated into, like, let's say 70% that we use for training, and then 30% of them reserved for testing and evaluation, if that makes sense.